This is Unit 10, Lesson 3, Vectors. Our lesson essential question is, how does including a direction with a quantity affect how you carry out operations on quantities? At the end of this lesson, you'll be able to interpret and use vectors for addition, subtraction, and scalar multiplication. Concept, vectors. A vector written as A with this little arrow over it is a quantity with both direction and magnitude. The direction of a vector is considered from the initial point to the terminal point, so where it starts to where it ends. The magnitude is the length of the vector and is written as the absolute value of the vector of A. So a vector can be used to determine the position of one point in space relative to another. Example 1, represent vector quantities. A plane is flying due north but is pushed off course by a crosswind blowing east. At 1 p.m., the plane is at the point 1010. At 2 p.m., the plane is at the point 100, 410. I want to find the speed of the wind and the speed of the plane due to its engine. How can you represent the change in the plane's location as a vector written in component and matrix form? So because the plane's path has both distance and direction, it is a vector. So here I start at my original point, 1010, and my terminal point, my ending point, is at 100, 410. Okay. The wind is responsible for the eastward change in the plane's location. So I subtract the x coordinates to find the amount of change, 100 minus 10, which equals 90. So the plane travels 90 miles east in 1 hour. The wind speed is 90 miles per hour. I found that by subtracting 410 minus 10, so my y values. So the plane's engine is responsible for the northward change in the plane's location. So I subtract the y coordinates to find the amount of change. 410 minus 10 equals 400. The plane travels 400 miles north in 1 hour. So the speed of the plane due to its engine is 400 miles per hour. The component form of a vector is represented by the coordinates x, y. Notice the brackets as opposed to normal parentheses or braces that we've used for matrices and things like that in the past. So this is actually, it's got more of a point to it. They describe the horizontal and vertical change of position from the initial point to the terminal point. In this case, the vector includes both eastward and northward changes. The vector AC represents a horizontal change of 90 miles and a vertical change of 400 miles. The change in the plane's location is 90, 400 in component form, and 90, 400 in matrix form. A plane is flying due north, but it is pushed off course by a crosswind blowing east at 1 p.m. The plane is at the point 1010, and at 2 p.m. the plane is at 100, 410. So this is the same problem we just dealt with. Now we're going to describe the direction the plane's heading, as well as how fast the plane's moving with respect to the ground. Okay, so the direction of the vector can be defined using an angle. So here's my angle, and I'm going to take the tangent, which is my opposite value over my adjacent value. Okay? Or in component form, when I have that component form, it's my y value over my x value. Or my x over my y, sorry. It's approximately 12.7. Calculate the magnitude of AC using the distance formula. So I take x2 minus x1 squared plus y2 minus y1 squared. In this case, it's 90 squared plus 400 squared, which is 410 miles per hour. The plane is traveling about 12.7 degrees east of north at a speed of 410 miles per hour in that direction. All right, let's try it. A vector has an initial point at 8,2 and a terminal point at 5,6. What is the vector component form and what are its magnitude and direction? So the first thing I've actually done is I've actually gone ahead and drawn my 2 points on the board and I've connected them with a triangle. Okay. So here's my initial point that they gave me, which was 8,2, and my terminal point, which was 5,6. So from this, they want me to write it in component form, find the magnitude and the direction. So the first thing that I want to do is figure out what my component form is going to be. So I'm going to take my x values and subtract them, and I'm going to take my y values and subtract them from each other. Okay? You start with the terminal point is your your first value. So in this case, I have 5, 6. So I'm going to take 5 minus 8, which is going to give me -3. And then I'm going to take my y value, 6 minus 2 equals 4. So my component is -3, 4. For my magnitude, I'm going to take the Pythagorean theorem, a squared plus b squared equals c squared. So this change we said was -3. This change was 4. Okay. So I'm going to take 3 squared, -3 squared plus 4 squared equals c squared. -3 squared is 9. 9 plus 4 is 16. So I have 25 equals c squared, which gives me 5 equals c. So my magnitude is 5. And then the last thing it wants me to figure out is my direction. So the direction, I'm going to take the inverse tangent. The inverse tangent of will be 4, -3. Which equals approximately -53.13. If you don't like the negative, which is fine, you can always subtract it from or add it to 360, and that'll give you a positive component. In this case, 360 plus -53 gives you 306.9, or approximately 306.9 degrees. Okay, so our component is magnitude's 5, and direction Example 2, understand vector addition. How can you add vectors v equals 4, 8, and w equals 3, -6 graphically and algebraically? Okay, so I can graph both vectors. So here's 4, 8, and 3, -6. Draw both vectors with an initial point at the origin, and then I can create a parallelogram. So I draw a copy of my w vector and with the terminal point at v, and then I draw a copy of v with my terminal point at w, and then I find the sum. So the terminal point of this copy is the fourth point d of the parallelogram, which is 7, 2. So the parallelogram rule states that if two vectors represent adjacent sides of a parallelogram, then the sum of the vectors is equal to the vector that is the diagonal of the parallelogram with the same initial point. The initial point of vector AD is the origin, and its terminal point is 7, 2. So the sum of vectors v and w is the vector AD with the component form 7, 2. You could also solve this algebraically, which I think is much easier to do. All you do is you add the x values and then you add the y values together, and that's your new point. So the components of vector AD can also be found algebraically by adding the components of v, 4, 8, and vector w, 3, -6. Adding the vectors together graphically or algebraically results in the same sum. Vector AD equals 7, 2. 4 plus 3 is 7. 8 plus -6 is 2. All right, so let's try it. I want to find the vector if mn equals 9, 12 and no equals 2, 7. What is mn plus no? So in order to do this, I'm just going to add my vectors together. So in this case, I have 9, 12 plus 2, 7. And that's going to equal vector 9 plus 2, 12 plus 7, which equals 9 plus 2 is 11, 12 plus 7 is 19. Okay. I can do the same for B. V equals negative 3, 4, and W equals 5, negative 8. So negative 3 plus 5, negative 3 plus 5, and then 4 plus negative 8. And that is going to equal 2, negative 4. All right, example 3, find the magnitude and direction of a sum. Paige is operating a boat across a river with engine speed set at 12 miles per hour headed 30 degrees south of east. The current of the river is 2 miles per hour at a direction that is 30 degrees west of south. What are the magnitude and direction of the path of her boat as she operates it across the river? So, step 1. Use trigonometry to find the component form of the vectors. So the boat engine, vector E, is going 12 miles per hour, magnitude at 30 degrees south of east. So here's my southeast. Okay. 12 sine 30 degrees, because here's my 30 degrees. Remember, this is my x value. So 12 sine, or my y value, 12 sine of negative 30 degrees, because I'm going down, is 6, and then 12 cosine 30 degrees is 6 square root of 3, or approximately 10.39. Since the vertical component is in the negative direction, my y value is going to be negative, so hence the negative 6. So the vector E is approximately 10.39, comma, negative 6. The current vector C is 2 miles per hour, magnitude at 30 degrees west of south. This vector makes a 60-degree angle with the horizontal axis. Find its component form in the same way. 2 sine 60 degrees equals the square root of 3, which is approximately 1.73, and 2 cosine of 60 degrees equals 1. Since both components are in the negative direction, my vector is negative 1, negative 1.73. My second step is to find the sum of the vectors that represent the boat's speed and the current of the river. Paige's actual speed is the sum of the two vectors, which is the diagonal of the parallelogram. So I do vector R, which is my actual speed, equals my vector E plus vector C. So 10.39 plus negative 1 and negative 6 plus negative 1.73 gives me 9.39 and negative 7.73. Step 3 is I find the magnitude of R. So I take those values, I square them, and then square root it. So I get approximately 12.2. Easy Pythagorean theorem. Okay, then I take the tangent, the inverse tangent of my y value over my x value. So my y value is 7.73 over my x value of 9.39, which gives me approximately 39.5 degrees. I can recall that the first component of the vector sum is positive and the second component is negative. Therefore, the vector that represents the direction of Paige's boat is in quadrant 4. Paige's boat went at a speed of about 12.2 miles per hour in the direction of about 40 degrees south of east. All right, so let's try it. If the engine speed is 9 miles per hour northwest at 135 degrees with the same current, 2 miles per hour at a direction that is 30 degrees west of south, what would be the magnitude and direction of the boat speed? Round the magnitude and angle of direction to the nearest tenth. So we're going to be doing something very similar to what we just did. Instead of 12, we're going to be using 9, and instead of 30, we have 135. So 135 is not pretty, and it won't give us a nice, lovely triangle with a 90-degree angle. So what we can do is we're going to go ahead and draw this so you can see it. Here's my compass. So this is north, northeast, south, west. Okay. So it told me that I was going 9 miles per hour northwest. So here's northwest. I'm going this way. Here's my vector. Okay. And it goes from here. So that is 135. Okay. What I can do is I can actually subtract 90 from this, so I can figure out what this angle right here is between the vertical axis and my vector. In this case, this is actually 45 degrees, and that's where I'm going to make my triangle. So it's easier to see. Okay. Okay. So this gives me my triangle. And then, of course, my current has stayed the same. It's going in this direction, and it's that 30-degree angle and everything. That's that 2 miles per hour. So what I get when I do this is I get 9 sine 45, and then I get 9 cosine of 45. Okay. So now when I'm finding this, 9 sine of 45 degrees equals about 6.36. 9 cosine of 45 is also about 6.36. Okay, so I'm going northwest, so my x value is going to be negative, just so we know. So when I write this in component form, I have negative 6.36, positive 6.36. Okay. From here, I'm going to take, so this was E, that's my engine. My C is going to stay the exact same from the from the previous example. So my vector for C is going to stay -1, -1.73, because that didn't change. That 2 miles per hour at a 30-degree angle, that didn't change. Okay. So now I'm going to take this minus this and this minus this. So when I do that, I get negative 6.36 minus 1, 6.36 minus 1.73, which gives me negative 7.36, 4.63. Okay. Now I'm going to take these, I'm going to square them and then square root that. So I get the square root of negative 7.36 squared plus 4.63 squared. Okay. That gives me the square root of 75.61, which is approximately 8.7 miles. That's my magnitude, so 8.7 miles. So I found my component, I squared these, square rooted it, which gives me my magnitude. My direction, I'm going to take the inverse tangent of my y value, 4.63, and my x value, negative 7.36. This is going to give me approximately negative 32.17. I don't like negative numbers. Okay. I'm going to subtract 180 in order to get it, or I'm going to add 180. So this is also 148. Add a 180, it's 148. It's going northwest. Example 4, understand vector subtraction. How can you subtract vector v minus vector w graphically and algebraically when vector v equals 6, 2 and vector w equals 0, negative 4? What are the components, magnitude, and direction of vector v minus vector w? The graph of v minus w can be found in a similar way to the graph of the sum of two vectors. In order to subtract w at its additive inverse, negative w, a vector with the same magnitude but opposite direction. The terminal point of v minus w is 6, 6, so its component form is 6, 6. The component of vector v minus vector w can also be found algebraically by subtracting the components of vector v, 6, 2, and vector w, 0, negative 4. 6 plus 0, 2 plus 4 gives me 6 and 6. The direction of the difference is theta equals the inverse tangent 6 over 6 or 45 degrees. The magnitude of vector v minus vector w is the square root of 6 squared plus 6 squared, which equals the square root of 72, which is about 8.5. Subtracting the vectors graphically or algebraically results in the same difference, vector v minus vector w, which equals 6, 6. The magnitude of vector v minus vector w is about 8.5, and its direction is 45 degrees. All right, let's try it. What are the components, magnitude, and direction of vector s minus vector t, where s is 6, negative 3, and t is 3, 2? So I'm going to do the exact same thing that I did with addition. I'm just going to subtract the values. So I get 6 minus 3, negative 3 minus 2 equals 3, negative 5. Okay, the magnitude, I'm going to take the square root of 3 squared plus 5 squared, which gives me the square root of 9 plus 25, which equals the square root of 4, which is approximately 5.83. And then my direction equals theta equals tangent, inverse tangent of negative 5 over 3, which equals negative 59 degrees or 301 degrees. For b, for the vector m equals 1, negative 3, and vector n is negative 2, 7. So I get a component of (1 minus 2), negative 3 minus 7, which is going to equal 1 minus negative 2. Sorry, 1 minus negative 2 equals negative 3 minus 7. So 1 minus a negative 2 gives me a positive 3. Negative 3 minus 7 gives me a negative 10. Okay. My magnitude, I just needed to figure out my component. Example 5, multiply a vector by a scalar. Multiply each vector by the given scalar. How do the magnitude and direction of the product compare to the original vector? So the vector r equals 9, 3, and my scalar is 5. So to multiply a vector by a scalar, I multiply each of the components of the vector by that scalar. So in this case, it's 5. I multiply 5 times 9 and 5 times 3. So I get 45 and 15. I can drag the slider to 5. Here, 2, 3, 4. Oops, too far. Okay. To see the scaled vector. While the direction does not change, the magnitude is increased by a factor of the scalar. So I multiply whatever I would get from my magnitude by 5 in this case, which is my scalar. So I find the magnitude the same way. Absolute value are the square root of 9 squared plus 3 squared, which gives me 90, square root of 90 times 5. You could also just do the component, which is 45 squared plus 15 squared, and you'll get the same answer. Okay? In order to find my direction, okay, doesn't change. I take the tangent, the inverse tangent of 3, 9 or 15, 45. I'll get the same answer. In this case, it's approximately 18.4 degrees. So the scalar product 5 vector r equals 45, 15 has the same direction and 5 times the magnitude of the vector of r. Multiply each vector by the given scalar. How do the magnitude and direction of the product compare to the original vector? So I have vector s is 4, 5, and my scalar is -3. So I find new vector components, multiply same thing by -3. So I get -12, -15. So you can see it just goes in the opposite direction. Okay, so there's -3. So here's my original. It's just going in the opposite direction because I multiplied by a negative number. My magnitude is, I just multiply by 3 out in front. So I want to take that absolute value of it. You can do the original vector, or you can just use the new vector, that the component vector that you've created, -12, -15. Again, both times you'll get 19.2. From there, you need to find the direction. So I'm still going to take the inverse tangent. It's going to be the exact same whether I use the original components or if I use the components that have been multiplied by the scalar. So in this case, 5/4 equals 51.3. And so these are both negative, so I get 231.3. So the scalar product -3 vector s equals -12, -15 has the opposite direction and 3 times the magnitude of s, of the vector s. So the original was 51.3. The new one is 231.3, just because it's going in the opposite direction. The magnitude of the resulting vector after scalar multiplication is the product of the magnitude of the original vector and the absolute value of the scalar. The direction of the resulting vector is the same unless the sign of the scalar is negative. And then the resulting vector differs by 180 degrees. Let's try it. If vector t equals -5, -7, what are the components, magnitude, and direction of -4t? So I'm going to take -4 times my vector. In this case, -5, -7. And that's going to give me -4 times -5 times -4 times -7, which will give me 28. So that is my component. My magnitude, I'm going to take the absolute value of -4 times the absolute value, the square root of 20 5 squared plus 7 squared equals 4 times the square root of 74, which approximately equals 34.4. Again, you can do the same. Instead of putting that -4 out in front, you can just do the square root of 20 times the square root of 20, or plus the square root of 28 and square that. You'll get 34.4. Okay, and then my direction is theta equals inverse tangent of 28/20, which gives me 54.5 degrees. Okay, I'm going to do the same thing with 2 times t. So I'm taking 2 times the vector -5, -7. So that's going to give me 2 times -5, 2 times -7. So equals -10, -14. Magnitude. I'm going to take the square root of -10 squared plus -14 squared gives me 100 plus 196, which equals the square root of 290, which is approximately 17.2. Okay, my direction is theta equals inverse tangent of -14 over -10, which equals 54.3. All right, example 6. Use matrices to transform a vector. How can you use matrix multiplication to transform each vector by the given transformation? I want to rotate vector AB, which equals 7, 9 by 180 degrees around the origin using matrices. So the matrix used to rotate a vector 180 degrees around the origin will change each point x, y to -x, -y. So the matrix that does that is T equals -1, 0, 0, -1. So when I multiply that matrix by 7, 9, I get -7, -9. Okay. Magnitude of the image is the same and the direction is the opposite of the direction of the original vector. Notice that the effect of multiplying 7, 9 by the matrix -1, 0, 0, -1 is to multiply each component of the vector by -1. This result is another vector equal in magnitude but with opposite direction. How can you use matrix multiplication to transform each vector by the given transformation? For B, reflect vector CD, which equals 6, 2, across the x-axis using matrices. So if I'm multiplying it, or if I'm reflecting it across the x-axis, that means I need my x to change from positive to negative. So in order to do that, so when I reflect my x doesn't change, my y value changes from positive to negative. So the matrix that does this is T equals 1, 0, 0, -1. So this would represent my y, this represents my x. So I take that matrix times 6, 2, which gives me 6, -2. The magnitude of the image is the same, but the direction of the vector is changed by reflection across the x-axis. Notice that the effect of multiplying 6, 2 by the matrix 1, 0, 0, -1 is to multiply the second component of the vector by -1. This results in another vector equal in magnitude, but reflected over the x-axis. All right, let's try it. Let vector EF, which equals 5, 10. How is vector EF transformed when it is multiplied by a matrix -1, 0, 0, 1? Okay, so when I'm doing this, I notice my y value is not changing, but my x value is becoming negative. So what that means is I've actually flipped. So here, if my image was over here, I flipped it over my y-axis. So in this case, reflected across the y-axis. So you can actually see this by -1, 0, 0, 1, and then multiply that by 5, 10. So you will get a vector of -5. How is EF transformed when it is multiplied by the matrix 0, -1, 1, 0? So again, I can go ahead and just multiply this. 0, and I'm multiplying it by the vector 5, 10. Okay, so when I do this, I get -10, 5. is my new vector. Okay, so what I've done is I've rotated 90 degrees counterclockwise. So clock normally goes this way, so I went this way. So basically I took my vector and I rotated one quadrant over. So it flipped my x and y, and my new x value became negative and my new y value stayed positive. So this was a rotation 90 degrees clockwise out the origin. Concept summary, vectors. In words, a vector is a quantity that has both magnitude and direction. Vectors may be labeled as vector v or vector AB. The components of a vector are x and y, noted vector v equals xy. Remember, it's not parentheses, it's those little weird brackets. When I graph magnitude, I'm graphing the absolute value of vector v, so I'm taking the square root of x squared plus y squared. And my direction, I'm taking an inverse tangent of y2 minus y1 over x2 minus x1. Operations, I can have scalar multiplication, so I just multiply a number by each of my vector components. I can do the same thing with addition. I just add the x values together and the y values together. And I do the same thing for subtraction, where I subtract the x values and I subtract the y values. And that is the end of Unit 10, Lesson 3.